room. Thus, we're having our keynote speech from our speaker all the way from Texas, Erik Welch, our senior system software engineer from NVIDIA. He has over 20 plus experience, and he has been, his first told me he has been with programming Python for more than 20 years, since Python 2.1. So let's welcome Erik about accelerating NetworkX fast graphic analytics with Python. Erik, please.
That introduction. I'm so excited to be here and so happy to be the one to welcome you to the conference with a presentation. I know they were going to just welcome this. I get to dive into some fun technical topics. I love technical talks. I'm going to talk to you about accelerating NetworkX. This is work that I'm doing at NVIDIA, but it's also a story of open source collaboration. We try to be good collaborators with open source, like we're solving problems that are win-win-win for everybody. So just to establish a level set of what is NetworkX, because I'm going to be talking about it. They say that NetworkX is a Python package for the creation, manipulation, and study of the structure, dynamics, and functions of complex networks. That is a mouthful. But basically, we make graphs. Code on the left creates a graph, adds 4 different edges between 4 different nodes, and we ask what is the shortest path between A and B. These edges have numeric weights, and it defines to go A to D, you go A, B, and D. It's a cost of 6. So let me more fully introduce myself before I get really into this talk. Hi again. Erik Welch, find me on LinkedIn or GitHub. And yeah, I've been doing Python for a long time, since Python 2.1. This is the version of Python that introduced the rich comparisons, such as Dunder LT for less than. And it's wild to think that that was a new feature. I have a very technical education. My background is in physics and computer science. And my career is sort of broken up into 2 different phases. I was a practitioner for the first 10 years or so, where I worked with other scientists and engineers doing a variety of things. And I have my data of my own that I work with. I'm doing my own analyses, and I really just love that there are these open source tools that can help me do my job. And in the last 10 years, I've been made this transition to be open source developer. So rather than having my own data, I make the tools for the data. And I'm very much in the high data, sci-fi spaces. I'm currently at NVIDIA on the RAPIDS team, where our goal is we make GPU accelerated data science with open source. We have a strong alignment. I identify as an open source developer first. NVIDIA, wait a second, but yes. Some major contributions I made throughout the years were recently, of course, NetworkX. cuGraph is NVIDIA's library of NetworkX. GraphBlas I'll talk about briefly. I've been a Dask and distributed contributor from the beginning. This is for doing parallel or distributed computation, and tools and site tools are popular functional programming. So talk to me about functional programming in the whole way. And being around as long as I have, it's fun to just make little contributions to projects that I'm very happy to use, like CPython, IPython, and so on. So I love technical talks, like I said before, and even if you're not that into graphs, I hope you can be interested in the theme of this talk, which is largely about connecting communities and trying to do something simple but bold. And I draw the ID here with 3 nodes, so I'm drawing a graph. On the top is NetworkX all alone. On the bottom is fast hardware, of which NVIDIA GPUs is one type of fast hardware, it's not the only one, and graph researchers. And largely, these groups don't really interact that much, especially with NetworkX. Graph researchers obviously like to make things fast, and they use GPUs. So our work today is to, figure out how to make these connections. How do we leverage the expertise of the graph researchers to make hardware fast and use it to users. This idea first came about to do this work last year at PyCon US, where I bumped into one of the core NetworkX developers, and we talked for hours and hours and hours, and coming down and forth like, yes, this is a good idea. And at another conference a few months later, I got my boss in the room, more of the NetworkX team in the room. We sat down and said, like, hey, do we actually want to do this? And there was a firm like, yeah, let's give it a try. But of course, like, why do we want to even do this? Because NetworkX has users. I did a survey of graph libraries a few years ago, and it was very depressing to see all the work that graph users do. They publish a paper, and then the software library it's there, it sits, it stalls out, it dies. Or it's useful as a reference, but it's not used, and so it's used. And how many users? NetworkX is really, really popular, it turns out. So 31.8 million downloads from PyPI alone just last month. This is a lot, this is big. And even if a lot of these are from continuous integration, doing testing, then that's a measure that NetworkX is used by a lot of libraries. So however you slice and dice this, like it's heavily used, which is great. So why do we say it's kind of an easy thing to say, let's try to do this, but why is it also actually hard to do? It's because like these communities that we're bridging, they don't really interact. And a Python user, they're very interesting. They have places to be and things to do. And sometimes one of those things is doing graph analytics. And when they do, they use NetworkX almost a certain way because it's trusted, it works. Until it gets too slow, in which case they may just live with it, it's very painful, or just don't do the problem, or try to find another solution. But this is not an uncommon story. People use it and then find out what do I do now. Whereas a graph researcher at, like, say, a national lab, they do graph analytics like all the time, all day, every day. So I think their life is probably figuring out infrastructure, and it sounds very stressful to me. And if you ask them, what do you think of NetworkX? A not uncommon reply is, what's NetworkX? And this is based on a true story, by the way, not quite that image, but the message. So let's jump ahead and like take a sneak peek of what we want the end state to look like. And this is actually where what things look like today. So we are adding backends to NetworkX, and so we don't want to change the default behavior of NetworkX. So if you use and love NetworkX today, great, nothing changes. But if you want to like make things faster, you can install a backend and now just use it in a number of different ways. It's always opt-in right now. Like you have to install it. You have to say like backend equals GraphBlas, which is a CPU backend that's faster. Or like in the first one here, it uses the NetworkX graph, converts it just for the algorithm, computes the page rank and returns. The second one, when you create the graph, we never even create a NetworkX graph, we're creating a backend graph. We're going straight from a pandas edge list to a cuGraph graph. Now that graph lives on the GPU. And so because it's on the GPU, it should be really fast. The third option that we do actually support, I'm not going to show how they do it, is like to automatically use backends if it's available for this algorithm. And we're going to make this better. We want to introduce a thing like we're calling autograph to automatically like convert between backend graphs efficiently and caching as necessary. And again, like I feel like I haven't even said, but why do we care about graphs? Well, do you have data? Does your data have relationships? And probably. And you want to gain insights from your data. Most of us do. Some examples are like, what is the most important node? Or what's the most central node? Or unusual node might be like, let's detect fraud. Like this person contacted that person, that's very unusual. Or they had this transaction, that could be fraudulent behavior. So important centralities and is it common class. Detecting communities, like maybe you want to download Twitter data or X data and figure out like what's happening in online networks. If you have a product, like, oh, this person looked at this, they bought that, can you recommend a product? Like, yeah, all these relationships of actions, what happens between users and systems and products. Maybe it's a movie recommendation. There's like, hey, you know, you and this person has a lot of connections in common. Maybe you should actually connect, and so on. Like I could spend the entire talk just talking about use cases for graphs because it's so varied. Not even talk about like creating features for data science or graph neural networks. And graphs are used by virtually all science and engineering fields. So hopefully you can see it. Yeah, it's used. Maybe you haven't used it or haven't used it much. And so why do we want to even make it faster? Because, you know, NetworkX is a data tool, and unless you've been asleep for the last decade, data is getting bigger. It's fun saying obvious things. And I want people to view NetworkX as a core data library Python, or tool in Python. And I mean by this, I want this to be viewed beside NumPy, oh no, and pandas, because NumPy is for array-like data, pandas is for data frames, and like people diffuse data if you use these libraries. But what about NetworkX? I want it to be like in the same paragraph. I want this to be in the same community, in the same clique as these two. And NetworkX is maybe a bit different. Like even if you use NetworkX today, it's like, wait, this is weird. But why is it weird? Because NetworkX is pure Python. And because it's pure Python, it is slow. Imagine if NumPy or pandas was pure Python and was hundreds or thousands of times slower. What, you know, happens virtually instant today might take you minutes or hours, or if it's, you know, something intensive, it might take days. And you probably wouldn't use NumPy or pandas if this was the case, but people still use NetworkX because it's what they have. So in order for NetworkX to be thought of as a core data library Python, like NumPy and pandas, it needs to evolve to support binary data structures with native performance. But how do we do that? Let's understand what it does today as a pure Python library. So it is extremely dynamic and flexible because it is comprised of, like, the edge data is a dict of dicts of dicts. So the source node and has a subdictionary of destination nodes, which has a subdictionary of like the edge properties. And the edge properties are usually numeric, they can be string, they could be anything. Nodes can be anything. And so it's very hard to say, oh, we can support anything and as a binary data structure, but maybe just supporting numeric stuff, common patterns is good enough to get us very far. So being pure Python is a strength because it's so flexible. And if you are adding and removing a lot of stuff, it's actually a very efficient data structure if it's rapidly changing. But usually you just want to run an algorithm on it and it's not changing within the algorithm. And it's a strength and weakness is that of Python, because Python is single-threaded and it's going to be slow. You can't use parallel computers yet or multi-core. So I like to view NetworkX as a great reference implementation, which is not necessarily a bad thing, because this has allowed it to be the API of users and is developed by the community. So it's a package that has spent roughly 20 years just figuring out what is the API that people want for a graph library. And that is like a goal for somebody who wants to implement algorithms, like because you already have an API to target. So yeah, it's very popular, lots of stars, a whole bunch of downloads, configures, algorithms, and equally importantly, like, you can learn about it, how to use it, and find questions, answers to questions like from Stack Overflow, and so on. So people use it because it's mature and battle tested and bug vetted, so it's trusted. But since it is a community, NetworkX core team asks do surveys, what do you want NetworkX to improve? Any thoughts? Who was the answer? You want to guess? The top response from the survey, not surprisingly, is users want NetworkX to be faster. If you've been paying attention, shouldn't be surprised. And we of us in the Rapids team at NVIDIA are not surprised by this. This is kind of our wheelhouse. This is what we expect users to expect. We want users to expect their data analytics workflows to be able to be accelerated. It's yes, I have this workflow, I want it to be fast, whatever that means for that particular workload. And I give NVIDIA credit because we show up and we work hard to make this happen. And this means different things for different libraries. So we help support cuPy, which is like NumPy. There's cuDF, which is like pandas. And NetworkX, we are building cuGraph, which is like NetworkX, but we're also now saying, hey, let's just use NetworkX directly. So how we do this in the Rapids, these are the things for different packages. So how we use NetworkX directly is via dispatching and conversions. So the user experience remains the same. You call NetworkX, use the API you know and love, needs documentation to create, and it will be able to use a backend. Which backend? It's up to you. So there's nothing NVIDIA specific about this. This is a win-win for everybody. You just need to show up and do this. Or maybe you have your own backend you're going to do privately. That's okay. And as a backend implementer, I can't express how nice it is to be able to already have an API to program to and already have documentation. I don't need to write documentation. I don't even need to write tests. Backends run NetworkX tests. We have infrastructure in place to make that happen. So users can trust the results still. This is a collaborative way for us to win and win and win. So on the left here we have the NX cuGraph. That's the GPU-enabled one on NVIDIA. GraphBlas algorithms uses GraphBlas. This is a library that comes from the graph research community, and it expresses graph algorithms in the language of sparse linear algebra. And so it gives us primitives with which to build graph algorithms. So it seems like a natural match for NetworkX. The NetworkX team is working on a parallel version where they want the graphs to be, still pure Python, but sometimes there's trivial loop that they can just make in parallel. It's still a work in progress. Other backends are possible, like sci-fi sparse, which is probably a good idea. So let's take a broad look about what is dispatching, just in general. Broadly, dispatching means choosing which implementation to run based on the type of the input arguments. And polymorphism is a common and special type of dispatching. And what I mean by polymorphism is just using the same method name. So cat.speak and dog.speak. You go with the cat class and the dog class. Both define the speak method, but they do different things and they're actually different functions. So meow and woof. There's a more functional approach with dispatching in Python. This is in the core library func tools, added a single dispatch. So let's say you have a duck class that does not define a speak method. So you make a speak function that can accept a class. And the default implementation say, okay, just call the .speak on the object. But in the duck, we define down in the lower left, you're going to do a quack. So make the cat speak cat, meow, speak duck, quack. And other libraries like Dask use multiple dispatch, which does the same pattern, but with multiple input argument types. So what does dispatching look like in NetworkX? Well, we're not going to understand this in this talk, and it gets more complicated than this even. But every single algorithm in NetworkX, we had to painstakingly add information, like programmatic information, that describes the graph data that is used in that algorithm. So, for example, connected components, like which nodes in the graph are connected. That doesn't use any node data, it doesn't use any edge data, it just uses the graph structure data. So that's just the simplest index dispatch. But PageRank does use one edge property. And so we have the edge adders there, we say, use weights. And ktrust returns a graph. And so we preserve everything that's on the graph, be it the node data, edge data, min cost, flow cost. This is a more complicated. It uses multiple edge attributes and node attributes. And things get more complicated from here, but with this metadata, it gives us a lot of power to work well with the backends. So let's look at a hand-selected benchmarks where, let's look at the upper right first. Between the centrality basically runs shortest path from the k number of nodes. So like here we're running shortest path, or single shortest, all pair shortest path from 1,000 randomly selected nodes, and it measures how many shortest paths went through any given node. And so with this graph with 3 million nodes and 16.5 million edges, we call it on the GPU, and with pure NetworkX, it runs in 2.5 hours. This is real pain. Like, do you want to say, hey boss, I'm running this algorithm, I'll get back to you in 3 hours? Probably not. Or we actually have a job to do. I'm like, I need this answer. This isn't TV. But with cuGraph, even with converting it to the data, like moving it to the GPU, it ran in just a matter of seconds, like 14 seconds. This is more than 600 times faster. And we could doctor this up to make it even look nicer, like don't do the conversion or like use different data. So the lower left version algorithm, this is a hand-selected. It's not typical, but even on the CPU version, using GraphBlas, square clustering is a measure of how many squares a node is involved with, and trust me, it's useful sometimes. NetworkX ran for days and days and days. Like, I was wondering whether I should kill it. Whereas with this backend, with GraphBlas, it was less than a minute. So it still took a few seconds, but days to, I'll just check my Twitter for a second. So it's 89,000 times faster. But typically, you can expect it to be hundreds or thousands or even tens of thousands of times faster. And this is transformative. This allows problems to be done that you couldn't do before. This makes people just so much more pleasant. So wrapping up, accelerated NetworkX is usable today with different backends. And we have 2 backends, 1 GPU, 1 CPU. And this is only for a limited number of algorithms. We are adding more. Like, I'm adding more to both of these actually every week. I recommend using the latest version of NetworkX 3.2 because we're working with the NetworkX team with this to help make things better. And you still need to opt in. We hope someday you will be able to just automatically, like, if it's installed, we'll use it. We have a lot more we want to do. Configuration, logging, conversion. I think it would be nice to just pass a pandas data frame directly to NetworkX algorithms and have that just work. My final thought is, like open source software, it's a way to collectively solve problems. And if you have an idea, whether it's a small idea, a big idea, just don't be afraid to talk about it and don't be afraid to contribute. Like, this is a simple idea that is hard to do, but everybody seems to be into it. So thank you very much.
Thank you very much, Eric. We are opening questions to the floor. Do we have any questions? There are 5 minutes Q&A here. And does anybody have questions? I think pass the mic. Michael was saying that which was the one that had the question? Sorry.
I can just yell it.
Okay.
I was just curious, how many cores and stuff you're parallelizing on for the CPU and
Oh, the question was how many cores is that parallelizing on with a CPU? The previous one, this was on a NVIDIA DGX, still NVIDIA hardware. So this was what, 40 cores, I think? And even like, it's nice to be able to leverage all the cores you have available, right? So the advantage of expressing graph algorithm in the language of linear algebra is that, yeah, your primitives are it's a sparse matrix and a sparse vector. And if you multiply that, hey, guess what? Computer scientists are really good at making matrix operations look parallel. And cuGraph, also, like the core team that does that in CUDA, they use similar primitives to like what's done in GraphBlas. But they choose primitives that make sense on the GPU. And of course, the GPU is super parallel as well.
so you're doing more than just straight parallelization now. It's not 40 times faster, it's 89,000.
Oh yeah, it's more than just like parallelizing it. It's like these are native data structures. So view it as like we convert the data into NumPy arrays or like CuPy arrays on the GPU. And so rather than every Python object where you need to like unreference, look up, like it's much more efficient and compact.
Do we have another question from the floor?
So with currently NetworkX is basically being revamped to accelerate, but I think there's been like the idea that a lot of the researchers are still using R. So would also on the side of also accelerating, would people in NVIDIA also considering basically transferring some of the algorithms and the other works from that already is pre-established from like iGraph and other R libraries to basically port it back into Python?
iGraph has bindings to multiple languages, including R and Python.
And also there's like CINNA and other like centrality graphs, for example. There should be like more applications as well.
Yeah, and there are other centrality applications. Repeating the question or statement. I would answer, if you have a particular need, like if you have a request, like we are all ears. Like we want to be driven by user requests. I want to hear what people need to use. This is also opening up a brand new epoch for NetworkX where say, hey, maybe we can add algorithms that we otherwise couldn't do before. Like maybe we could have this backend specific or only algorithms because like nobody should do this in pure Python, but you can do this with other libraries. Thanks for the question.
Thanks, Eric, for the great talk and very impressive on the performance quiz from the cuGraph. But I'm curious because I'm not coming from a data science background, but more on the platform side. I'm aware there is some of the like Neo4j or some of the Spark, they have their also graph analytics. Just curious, like when people working with data with like big network, when will we going to use the NetworkX, but when are we going to use the like GraphX or the Neo4j? And yeah, just curious on that.
Yeah, so there are two kind of technologies there. One was a graph database like Neo4j. And if you want your data in a graph database and doing graph queries using their query language, and if you're, this is good if you're a business user with like business queries or like follow this and log this way. And I know that you have algorithms. I actually think it would be interesting to have a database backend to NetworkX So let's do it. It asks for why would you use NetworkX instead, just to connect to where your data is. Like you could also say, hey, why do we need pandas if you can just use any number of databases? Because sometimes just you want to load the data in memory, and you don't care about all the stuff that the database gives you, and you just want to operate on that right there. As for the Spark, the GraphX runs on Spark and is distributed. I would, well, if you benchmark that, perform that, it's not very fast. And I don't know if it's well maintained and developed. I don't want to be too critical of anybody as I of working on that. I will say comment about cuGraph that it is infinitely scalable. So if you have a massive graph, like you have a government data or social network data, like with cuGraph, we've run PageRank on a 1 trillion edge graph in a matter of like 24 seconds, I think. And this is because, like, this is on thousands of GPUs, and the memory bandwidth between GPUs is so much faster than you can get between just connecting CPUs. So, great C question, again. Thank you.
I think we can take one more question from the floor. Any other questions?
Thank you for the presentation. What I'm asking is why do you choose to adopt pandas data frame while pandas maybe has some problems right now? There is all the pandas is moving to polars or something like using Apache Arrow or Parquet or other compressed columnar storage. Why are you looking for data frame?
Okay, I think that's actually a fun question, and I would sort of pivot it first and say, the question, what if pandas work on their API for 20 years first, and then say how to make this fast, and like doing the same kind of dispatching that we're doing, so you wouldn't have all these different data frame libraries that are doing things slightly differently, and hey, like we're better or faster, this or that. But I gave it as an example because it is something people know, and it makes, like, and there's nothing preventing people from, like, hey, let's, like, if you passive a Polar's data frame, like, let's make the infrastructure flexible enough so that that can just work. Like, oh, we can convert that to a backend. So it's just, I think it's a nice way to just meet people where they are with respect to the toolings that they use. And a lot of people are able to load data into pandas data frames or like Dask data frames or other data frames. So yeah, Jen, show me your, give me your requests.
Thank you very much. I guess it's about time. I think if you have more questions, over here, I would be happy to answer your questions. So we'll have a break until 11.